So the next tool we'll be adding to our toolbox for finding the roots of a polynomial is a nice one. This is the one that actually tells us what the roots are. Well, it's not what the roots are so much. It tells us what the roots can be. It's going to give us a list of possibilities. And then it's up to us to go back and check them and see which ones actually are and which ones actually aren't. So I have a statement of the theorem here, and it's a little wordy, right? But it's not too bad once you start to dig into it. It says, look, if we have a polynomial and the coefficients are integers, right? So we're only looking at ones. Remember, integers 1, 2, 3, 4, 5, and the negatives, -1, -2, -3, and so on. Then it says every rational root. Rational roots, those are fractions, ones that look like P over Q, has to meet two conditions. The numerator is a factor of the constant term, and the denominator is a factor of the leading coefficient. That's the coefficient that's out in front. Okay, so again, this is one of those wordy ones. It's easier, I think, if we look at some examples, right? We'll see what's going on. So I have this polynomial here. And notice that you got to read the questions. I wasn't actually asked to find the rational roots. I was just asked to discuss them, right? I want to know what the possibilities are based on this theorem. What this theorem is saying is I have to look at all the factors of the constant term. The way I do this, I like to put them in a table. All right, so I'm going to put the factors of the constant term in the columns. And when we're talking about factors, I mean the positives as well as the negatives. All right, then I'm going to put the factors of the leading coefficient. I'm going to put those in the rows. So I'm going to have plus or minus 1, plus or minus 2, plus or minus 4. All right, those are all the factors of 4. Now I can answer my question. And remember, I need all of the fractions that I get from dividing factors of the constant term by factors of the leading coefficient. So I'm going to have plus or minus 2 divided by 1, plus or minus 1 divided by 1. Here, plus or minus 2 divided by 2, plus or minus 1 divided by 2. Plus or minus 2 divided by 4, plus or minus 1 divided by 4. Then when we're doing this, we often have a little cleanup we need to do. 1 divided by 1, that's just 1. 2 divided by 2, that's 1. 2/4 is 1/2. And 2 divided by 1 is 1. Then we often get some duplication with these. You notice plus or minus 1 showed up twice, so I'll cut one of those out. Plus or minus 1/2 also showed up twice. And now I've cleaned it up. The possible rational roots of this polynomial are plus or minus 2, plus or minus 1, plus or minus 1/2, and plus or minus 1/4. So this is the power of this theorem, right? It gives us a list, right? I know that the rational roots all have to come from that list. And some of the numbers will be, some of the numbers won't be, right? Obviously, this is a 5th degree polynomial. It has a maximum of 5 roots, and there's 8 numbers on my list. So all of them can't qualify, right? But some of them might. Right, so our next step, that's all this question asked for, right? This question just asked for a list. All right, let's go to the next one. The next one's going to ask us to take this a step further and actually factor the polynomial. All right, so I'm going to start with the same approach. I'm going to make a list, right? I'm going to put the factors of the numerator. I need a little room here. Let me do this further over. I'm going to do the factors of the constant term, Those go in the numerator of my fraction. That's the hardest part of this whole thing, is remembering which numbers go in the numerator and which ones go in the denominator. Then I got to do the factors of the leading coefficient. Well, that's also plus or minus 1 and plus or minus 2. All right, now I start dividing. This is 1 divided by 1, and this is 2 divided by 1. This is 1 divided by 2, and this is 2 divided by 2. All right, so that's just plus or minus 1. That's just plus or minus 2. And this one is also plus or minus 1, but we already got that, right? And I don't need to duplicate, so let's take that one out. Okay, so now, how do I tell which of these are good and which of these are not? Well, I'm going to use my factor theorem, right? My factor theorem says that a number is that a number is part of a factor only if p of that number is 0. Right, so what I'm going to do, I'm going to make a little table. I'm a math professor, I like tables. Right, I'm going to make a table. I'm going to put the x values here, 1 and minus 1, 2 and minus 2, 1/2 and minus 1/2. And then what I'm going to do over here is I'm going to say, what is p of x? The ones that come out to 0, those are my yeses. All right, so let's see. Now, this is just calculator work. P of 1, 2 times 1 to the third, plus 3 times 1 squared, minus 3 times 1, minus 2. You go to your calculator, you work this one out. That one comes out to 0. Excellent. 1 is a root. Now, remember, I'm going to need the factors, right? But we'll circle back around to getting the factors from the roots in a minute. Okay, so now you just keep testing, and I'm not going to make you sit here and make you watch me work all of these out. P of -1 is 0. If you go ahead and test these on your own, you can pause if you like, do the calculations. This is 72. This is 12. Obviously, I worked these out in advance. P of 1/2. And I did these as decimals because it was marginally easier. Well, I'm sorry. I was looking at the wrong one. P of -1 is 2. P of 2 is 20. P of -2 is 0. P of 1/2, that's -2.5. And P of -1/2 is 0. So now I found my 3 factors. Now remember how we go from roots to factors. Remember, if x equals 1 is a root, then x minus 1 is a factor. Similarly, if x minus 1 is a root, then x, let's do minus 2, right? Because minus 2 is our actual root. If x minus 2 is a root, then x plus 2 is a factor. And finally, if -1/2 is a root, then x plus 1/2 is a factor. And that's what I needed. 3 factors, right? This is a third-degree polynomial. It's going to have 3 factors. The factorization of this thing is x minus 1 times x plus 2 times x plus 1/2. Now, we've run into a little bit of a problem, right? If you go to test this, you will see that it doesn't work, right? If you try to multiply this thing out, if you multiply this out, just look at the first terms. We know where the first terms come from now, right? We remember from when we were talking about multiplicities and end behaviors. The first term is going to be this times this times this, and that's just x to the third, not 2x to the third. And if you multiply out the constant terms, minus 1 times 2 times 1/2 is only minus 1. Okay, so what's happening here? There's a little technicality. The the roots don't uniquely determine a polynomial, right? Because if you take a given polynomial and you multiply it by a number, if you multiply it by 5, the roots don't change. It looks different, the graph would be different, but the roots are the same. Okay, and that's what's going on here. Remember that our rational root theorem says the roots or the coefficients have to be integers, and that 1/2 is what's messing the whole thing up. All right, so what I'm going to do is I'm going to take my factorization here, and I'm going to say, look, I got an x to the third, I need a 2x to the third. I have a -1, I need a -2. That's telling me what that constant multiple is going to be, right? So if I take this polynomial and I multiply it by 2, now this would be 2x to the third and -2. Now it's going to work, right? So when you get to the end, you may have to make a little adjustment, right? And actually what I would do is I would take this 2 and I would multiply it into here, right? And I would say my final answer is x minus 1 times x plus 2 times 2x plus 1. And there's my factorization. You notice how that works, right? This, if I made this into an equation, this factor would give me -1/2 as a root, and this factor would also give me -1/2. It works in the end. Okay, so let me give you one. Right, try doing this one. Work through that process again. Go ahead and pause. Right, see if you can make a table, come up with the roots, test them, see what you end up with. Okay, so I'm going to make my list. Right, I'm going to start with the coefficients of the constant, the factors of the constant term. It's going to be plus or minus 1 and plus or minus 2. Then I need the coefficients of I keep saying coefficients, the factors of the leading coefficient. That's plus or minus 1, plus or minus 2, and plus or minus 3. All right, so let's see. I'm starting off with 1 over 1, which is just 1, and plus or minus 2 over 1, which is just 2. All right, so let's see. Here I get plus or minus 1/2. Then plus or minus 2 over 2. But look, 2 over 2 is 1. And I've already got plus or minus 1 on my list, so that one's a duplicate. Then plus or minus 1/3. And finally, plus or minus 2/3. And those are all unique, I think. There's, what, a total of 8 this time? So let's see, I'm going to do my thing again, right? And I'm a little short on room. So I'm actually going to do 2 tables, right? I'll just split it in 2. All right, so let's see, x's. I've got plus 1, minus 1, plus 2, minus 2, and I'm going to do p of x over here. And then let me do the fractions. 1/3, minus 1/3, 2/3, minus 2/3. Okay, now again, hopefully you tested these out, right? And you see this came out to, let's see, 0, 0, 72, 12, and I did these as decimals because it was a little easier on the calculator. Not 0, it's really all I care about, right? Not 0, negative 3.704, not 0. And this one does come out to 0. And now we just run into a little bit of a problem, right? The x equals 1 root gave me x minus 1 as a factor, and the x equals negative 1 root gave me x plus 1 as a factor, and finally the negative 2/3 root. Now watch how I do this. This is another way of thinking about how we can make sure we only get integers for the coefficients. If I set this equal to 0, I get 3x equals negative 2, 3x plus 2 equals 0. And there's my other factor, right? There's what my other factor would be without the fractions. And we've got a problem, right? There's a problem here. I've got a fourth degree polynomial and 3 factors. There need to be 4 factors. What's happening? I don't know, but here's how we can find out. Look, let's go through the process. Let's do the long division, right? Not the long. I'll do the synthetic division. But so I'm going to start with my polynomial 3, 5, negative 1, 5, and negative 2, and I'm going to divide this by. That got a little messy. I'm going to divide this by 1. All right, so let's see, bring down the 3. 3 plus 5 is 8. 1 times 8 is 8. Then I get minus 7, plus 7. Get a 1 up. 1 times 7 is 7. Did I mix up a sign somewhere? 3, 8, 3, 5, oh, that's a negative 5. There we go. So this is 2. 1 times 2 is 2, and that comes out to 0. It wasn't coming out to 0. That's how I knew I'd messed up somewhere. Okay, now, let's do it again. Let's do it with a minus 1. Divide that into this thing and see what I get. Well, again, bring down the 3. That's 3 times negative 1 is negative 3. 8 minus 3 is 5. Minus 1, 7 minus 1 is 6. Minus 1 times 6 is minus 6. And I needed that to come out to 0. Checking my arithmetic. 8 minus 3 is 5. What am I doing? That's a minus 5. So, right, minus 1 times 5 is minus 5. 7 minus 5 is 2. So this will be minus 2. And yes, excellent. That comes out to 0. Okay, now let's look at what we've got. That tells me the factorization is x plus 1 times x minus 1 times 3x squared plus 5x plus 2. Good. Now, that one I can factor manually, right? That one I can factor by hand. X plus 1, x minus 1. And I know one of my factors, you can cheat a little bit. I know one of my factors is going to be 3x plus 2. So what's the other one have to be? X plus 1. That's why we didn't see a fourth factor coming out of the rational root theorem. This x plus 1 factor was duplicated. Unfortunately, the rational root theorem doesn't give us doesn't really tell us that's going to happen. We kind of get a hint, right? When you get a situation like this, you know there's 4 roots and you only found 3. You should be highly suspicious that that's what's going to happen. But the only real way to find out for certain is to do this long division, right? Then you'll actually see the factorization is x plus 1 squared times x minus 1 times 3x plus 2. Okay, so that's the rational root theorem. The thing about the rational root theorem, I mean, you probably realized this as you were working on that last one, if you stopped and tried to do it by hand yourself. The rational root theorem gives us sometimes a fairly large number of possible roots. Now, I don't know if you were doing those by hand. I cheat. I do them in Excel, right? I make a list of the x values, and then I just do a formula to do the calculations, and it actually goes fairly quickly. What we're going to talk about in the next set of lectures is something called Descartes' rule of signs. And Descartes' rule isn't super informative in just as a standalone theorem, but when you combine it with the rational root theorem, what Descartes' rule does is it lets us rule things out, right? So you'll see sometimes we'll be able to say, well, we know there are no negative roots, so don't check those, right? Just check the positive ones, right? So that's going to be our next step, right? See if we can't get a theorem that's going to help us narrow down this list without kind of the pain of having to do an awful lot of calculations.